So this is a video which is a continuation of the derivation of the vibrating string. And where we left off was we found the spatial function, the function for the displacement with respect to position. And what we want to do is now figure out what the time dependence of this function is. And so what I can do is basically take a state defined as, the M space, which is related to what we have up here. So basically it's kind of the same thing, except for now we're operating in M space instead of position space, X. And if I project my M space onto my function, which is time dependent now, so the space which is dependent on the time, it's basically projecting the time space onto the M space, which is related to the position space. So if we go back to our original differential equation, then we had the acceleration, basically, the second derivative with respect to time of a particular projection, particular M in this space, which is equal to minus k squared times that original function right here. Now k squared, or k, we said it was m pi over L, so k squared is m squared pi squared over L squared. So we have this now, this differential equation with respect to time minus m squared pi squared over L squared, the original function back again, like so. So we can solve this with respect to time, and what we would get is that this particular function would be equal to some initial starting point, so time equals 0, times a cosine m pi L times the time. So again, it's a lot like the previous solution in position space. Now this is in time, and we've implied the initial condition that this function at time equals 0 has to be 0, and its speed at time equals 0 has to be 0. And that's what gives us the solution above. And so now what we want to do is to take off the particular M that we're projecting onto and have a general solution for the time-dependent function. So to do that, what we can do is basically sum over all possible M states. So M from 1 to infinity, like so. Basically the identity operator. And if we write this now in terms of that initial conditions, so at time equals 0 times the cosine of omega m t, where omega m is now m pi over L. Okay, so that gives us the propagator. The propagator is that operator which takes the initial state and transforms it into the final state. And in this case, it's the identity over M states times the cosine of omega times t. Okay, So now the interesting thing is we can apply the position basis to this time-dependent function, like so. And that's going to give us our final position and time-dependent displacement function. But let's write it in terms of the propagator. So we're starting at a time of 0. So t is equal to 0. We propagate with the propagator u of t. That gives us the time at some later time. And then we project it onto the position, on the position space. So that we could solve for with this integral from the length 0 to L. Do a change of basis. Dx, and then we integrate over dx prime. Now, the propagator operating on the position bases is the sum m equals 1 to infinity, x projected onto m projected onto x prime, cosine omega times t. And we could write this out in its full glory, because now we can write out those products of x and m, and we get, if I have enough space, square root of 2 over L sine m pi x over L, square root of 2 over L sine m pi x prime over L times the cosine of omega t. So multiply that in right there. So, we can clean up just a little bit and get the sum of 2 over L sine m pi x over L sine m prime, m pi x prime over L times the cosine of omega t, like so. So basically all we're doing is we're saying that, what we can do is we now take this propagator, u of t, and apply it to the initial condition, and we can get our function psi x at any time when we operate with u of t on our initial condition, x prime at some time t equals 0. And there we have our full-blown solution of how to start with some initial condition, initial position, initial time for our string, apply the propagator, select out whatever m state you want, and then you can pick out that vibrating string at that particular wavelength.